morning and a very warm welcome to all of you. I am Parameshwaran Sankaran. This year is IMSC. We are celebrating the golden jubilee year of IMSC, and as part of our outreach program, we have been having workshops at various levels, and in the past we have had workshops for school teachers, school students, and this one is the last in this series. It's for college lecturers. I have a few announcements to make before we can start. The tea will be served near the elevators on this floor in the morning and afternoon. Morning at 10:30, afternoon at 3 o'clock. There will be group photo around before 1 o'clock. So around 1 o'clock in front of the library we will all assemble for a group photo before lunch. Lunch will be served on the other side. We have this guest house complex across the road from here, from the institute. So that will be at 1 o'clock after the group photo. And there will be no formal chairpersons for various sessions. The speakers for today will be first by Professor Kesavan and then Amritanshu Prasad. He will talk on linear algebra, some topics in linear algebra. Then it will be followed by Vishwanath and Raghavan and also Jaya Iyer. So I will let them explain to you what they will, the title of their talks and what they will talk about and so on. I think I have said all that I wanted to say. One final thing is, I request all of you to switch off your mobiles or put it in silent mode so that the lecture can go on without interruption. Okay, I let now.
Thank you very much. So, I will be talking about some important partial differential equations. So, differential equations is in the heart of analysis. Everything changes in nature. Nature is constantly evolving, and differential equations tell you how things evolve. So, they are a very important class of important topic to study. And many of the topics in analysis came from the understanding of the methods of solving differential equations. Theory of summability, then notions of cardinality, set theory, Lebesgue integration. So many topics have all come because people wanted to understand the methods which they were using to solve differential equations. So in the 18th and 19th centuries, all the problems studied by Euler, Lagrange, all these people were problems of a practical nature, and they tried to solve some differential equations, and in the process many things got clarified and so on. Today I will look at some partial differential equations, which you know, of course, are differential equations involving derivatives in partial derivatives of functions of several variables. So we look at the Cauchy problem for a second order equation, which is of the form AUXX. The subscripts denote the derivatives, plus 2BUXY plus CUYY equals D. If A, B and C and D are just functions of the independent variables x and y, then you call this a linear equation. And the equation is called quasi-linear because it's linear in the highest order derivatives but not otherwise. So if these functions depend also on the dependent variable, namely u and its first derivatives. So what is a Cauchy problem? You take a smooth curve, parameterize by x equals fs, y equals gfs, and then you want to solve this differential equation subject to some prescribed data on this curve. So you can prescribe u equals h of s and the first derivatives with respect to x and y. But you can't do all of this arbitrarily, because h of s is u of fs gs, because if you substitute, u is h of s and then f and g are the parametric forms. So if you differentiate this, then you get h dash equals phi f dash plus c g dash, and so there is some kind of compatibility which all of them must have. So one cannot arbitrarily prescribe all the three functions. What one could do independently is prescribe u and the normal derivative along this curve, because the normal derivative will be a linear combination of ux and uy, and therefore you can prescribe that independently. But if you prescribe these three, then all of them cannot be prescribed independently. Now we go and first we have the equation itself, and then if we go back and differentiate this condition phi equals ux and c equals uy with respect to s, you get two more equations. F dash uxx equals plus g dash uxy equals phi dash, f dash uxy plus g dash uyy equals c dash. So if you want to compute the second derivatives on this curve uniquely, then the determinant, the unknowns are uxx, uyy and uxy. So if you want them to be determined properly, then this determinant should not vanish. So you say the curve is a characteristic curve if this determinant, which works out, if you calculate, it's ag dash square minus 2bf dash g dash plus cf dash square equals 0 for all points on it, and it is said to be non-characteristic if it's always non-zero, so that you can invert this. Now what's the point of all this? Because if I can invert, then I can compute the second derivatives. Now that is one foot of the camel into the tent. Once I can compute the second derivatives, I can iterate this procedure, compute third derivatives, fourth derivatives and so on. So in principle, I can compute all the derivatives. Then I can try to write the solution in a neighborhood of a point on the curve as a Taylor series, because I know all the derivatives. So all this is very formal, but one can prove a theorem. For instance, if the data is analytic and the curve is analytic, then of course this method actually works. So if you have a non-characteristic curve and Cauchy data, then you can hope to solve the problem uniquely, at least in the neighborhood of the solution. So if you have a characteristic curve, then of course those right hand side has to satisfy some compatibility conditions, because the determinant is 0 and therefore you cannot in general solve. So characteristic curves, if you prescribe data on them, you cannot solve. Now how to determine which are these characteristic curves? You have this equation, namely the determinant equal to 0, and you can rewrite it in terms of dy, because g dash is dy by ds and f dash is dx by ds. So if you rewrite it, then you get dy by dx equals b plus or minus root of b square minus ac by a. So if b square minus ac is less than 0, there are no characteristic curves at all, and we call this an elliptic equation. If it is 0, there is one real characteristic, we call it parabolic. If it is greater than 0, then there are two real characteristics and you call it a hyperbolic equation. So this is very similar to what you have been doing with conic sections. The terminology is the same. Ax square plus 2hxy plus by square equals 1. So that's a conic. It depends an ellipse if you have the determinant condition, if you have a parabola or a hyperbola, depending on how the determinant, which is exactly the same relation which we have here. We can do this in more than two variables also, so I don't want to get into the details of that, but this can be generalized. So again we classify second order quasi-linear equations as elliptic, hyperbolic and parabolic, and the three prototypes are the Laplace equation Laplacian u equals 0, or the Poisson's equation Laplacian u equals f. So that's a homogeneous equation, this is an inhomogeneous equation, or the heat equation which is parabolic, or the wave equation which is a hyperbolic equation. So Laplacian u of course is sigma d2u by dxi square. So this is the, so we can extend this. So what I want to do today is to give you a flavor as to how we go about solving these equations. I won't do the most general and all these things. I'll try to solve them in Rn, give the formulae, and then see, just looking at the solution, try to predict some of the properties of the solution. So that is the idea for today's lecture. So let us start with the Laplace equation, Laplacian u equal to 0. So then we call u as a harmonic function. Now this equation is rotation invariant. If you make a transformation of variables using an orthogonal matrix, a rotation in space, this equation won't change. So if the equation doesn't depend on the rotation of the axis, it is natural to expect a radial solution, because if you do polar coordinates you have r and theta. If something doesn't depend on theta, then you think it depends only on r. So the same thing in higher dimensions, only instead of theta you will have n minus 1 different variables. So we try to look for a solution in a radial solution which depends only on the length of the vector. So we go to polar coordinates, and this you certainly have done probably in the advanced calculus courses when you for your students. So in polar coordinates, if when we rewrite the Laplacian, and if you omit the theta part, namely the dependence on this spherical part, then only r will come in. So you get u double dash plus n minus 1 by r u dash equal to 0, where n is the dimension of the space. Okay. So we can solve that. U double dash by u dash is 1 minus n by r, so you can get u dash as c by r power n minus 1, and which will give you ur equals b log r plus c if n equals 2, and b by r to the n r power n minus 2 plus c if n is bigger than or equal to 3. It's a bit slightly bad notation here, sorry for that, and I should have put c here and b here, doesn't matter, they are all constants, they don't. We choose a particular value for b and c for a very specific reason. So you call this a fundamental solution. Phi of x is minus 1 by 2 pi log mod x if n equals 2, and n into n minus 2 alpha n mod x to the n minus 2 if n is bigger than or equal to 3 for x not 0. All this is defined only when x is not 0. There is a singularity at the origin, and alpha n is the volume of the unit ball in Rn, and the formula for alpha n is a very nice calculation. It is pi power n by 2 by gamma to the n by 2 plus 1, where gamma is the gamma function. So if you put n equals 2, you get gamma 2, which is 1 factorial, and therefore 1, and pi. So alpha 2 is pi, which is the area of the unit circle. If you took n equals 3 and work this out, you will get 4 by 3 pi, which is the volume of the unit ball in R3. Okay. So x to phi x is harmonic as long as x is not equal to 0. Away from the origin where the singularity is there, this function is a harmonic function because we solved the differential equation. And so if you translate the origin, we have x going to phi of x minus y is harmonic as long as x is not equal to y. So now if you multiply by a function in Rn, so x going to phi of x minus y fy, that doesn't depend on x. So this is again harmonic in x as a function of x as long as x is not equal to y. So if you take a finite sum of such functions, they will also be harmonic because the operator is linear, except at a finite number of points. If I take y1, y2, yn and so on, some n points, if you omit those n points, elsewhere this function is harmonic because each individually they are all harmonic. Then what can one say about the integral? Okay, integral is a limit of a sum in some case. So what do you say? Is this a harmonic function at all? Answer is no, it's very misleading. So we have the following theorem. Suppose f is a, you can simplify, these hypotheses are not the most general ones. I am just taking it for as an example. So if f is a twice differentiable function with compact support, that means it vanishes outside a compact set in Rn, then you define u integral Rn phi of x minus y fy dy. This integral is well defined because f has compact support, and therefore this integral can make sense. Then in fact u is a C2 function and Laplacian u equals f. So superposing all these harmonic functions on one on top of the other, we produce a solution of the Poisson's equation. So this is the Poisson's equation solution, and you can of course, as I said, for other f also this is true. You might have heard the word Green's function and so on, when dealing with PDEs. Green's function is just a modification of this fundamental solution here to take care of boundary conditions. So always the solution in the for the elliptic problem is given as a sort of convolution. This is a convolution product here, integral phi of x minus y fy dy, that is a convolution, and you get it. Okay, so let us see some interesting properties of this. So let omega be an open set and u is in C2, a harmonic function. Then for any x in omega and for any r such that the ball center x radius r is contained in omega, we have that ux is the average of uy on the sphere of radius r center x, which is also equal to the average of u over the entire ball center x radius r. So this is a very strong and nice property. So if you have a harmonic function, if at any point you take a ball round it and take the average of the function on the sphere or on the ball, it does not matter, you will recover the value at the center. Okay, this is like so this is and it's a very simple proof. It's just change a variable and then differentiate and then you use Gauss divergence theorem. There's only 3 lines in the proof. I've told you all the 3. Change it to, because you want, what you want to do, if we take phi of r as 1 over n times alpha n, this is the surface area, r power n minus 1 integral over the boundary of the ball, which is the sphere, u of y dsy. So if I make a change of variable, this can be become 1 by n alpha n integral the boundary of the unit ball of u of x plus r times psi. This is just a change of variable. Now if I want to do phi dashed of r, I can now differentiate. I can't differentiate here because this also depends on r. There is a boundary which is depending on r, and so it's difficult. So I change it to a fixed boundary and then differentiate. Then I get 1 by n alpha n into integral grad u of x plus r psi into psi ds. And then I go back. So this is 1 by n alpha n r power n minus 1 integral dB of xr of grad u of y, xi is y minus x by r ds1. Now here you have a gradient, and this is nothing but the unit normal on the surface of the sphere. X is the center, so the unit normal is just y minus x by r. So here you have exactly by the Gauss divergence theorem, this becomes n alpha n r power n minus 1 integral dB of Laplacian u ds by the Gauss divergence theorem, and we know u is harmonic, so this is 0. So phi is independent of r, so phi of r equals phi of 0, which is the integration over circle sphere of radius 0, and so that is just the value of the function. So you get. The other one is immediate from this, you can easily do that. Okay, and the thing is that the converse is also true. So let us see an immediate application of this. So if u is C2 in omega and C up to the closure, continuous in the closure, is a harmonic function, then the maximum of u is the same as the maximum on the boundary. The maximum in the whole domain is just the maximum on the boundary. And if omega is connected and u achieves its maximum at a point in the interior, then it has to be a constant function. So it tells you if you have a non-constant harmonic function, the maximum can never be achieved in the interior of the domain. The maximum is always achieved only on the boundary. So what's the proof? You take x naught such that inside the domain such that it achieves the maximum, then take any ball of radius r which is contained in omega. So r should be less than the distance of x naught from the boundary. Then m is ux naught equal to this, equal to sign missing here, which is the average in the ball 1 over alpha n xn b uy. But uy is less than or equal to m, and therefore if you take the average, that will also be less than or equal to m. So you have m on both sides, so you have equality throughout. So this is possible only if u is identically m in the ball. So if u achieves its maximum at a point in the interior, it achieves its maximum in a neighborhood. So the set of all points where u achieves its maximum is an open set. But because u is continuous, it is also a closed set. A set can be open and closed in a connected space only if it is the whole thing. It is non-empty, we know that, and therefore it has to be there. So this proves the second statement, and therefore the first statement follows from this. So this is a very useful, maximum principles are very useful properties of elliptic solutions of elliptic PDE, and a lot of geometric results and many estimates for the sizes of the solution. Many things can be got from the maximum principles. It's a very powerful tool. So one important consequence of the maximum principle is the uniqueness for the Dirichlet problem. Dirichlet problem means you prescribe u on the boundary. So omega is a bounded domain, and consider minus Laplace in u equals f in omega, and u is given on the g on the boundary. So if these are continuous functions, then in this class of C2 intersection C, you have only one solution, because if you have two solutions, then the difference Laplacian u will be 0 and u will be 0 on the boundary. But you know that if it achieves the maximum in the interior, then it has to be a constant, and since it is 0, since it's 0 on the boundary, so u1 minus u2 has to be less than or equal to 0. So the function will achieve its maximum only on the boundary, which is 0. So u1 minus u2 is less than or equal to 0. And now you change the roles of u1 and u2, do the same thing. So you get u2 minus u1 is also less than or equal to 0. So u1 is identically equal to u2. So a very simple consequence of the maximum principle is the uniqueness of the solution to a Dirichlet problem. Whenever we look at PDEs, we look at, or even ODEs, we look at three things. Does there exist a solution? Is the solution unique? And the third one is a little more complicated question. Does the solution depend continuously on the data in some suitable topology? Okay. If all these three are there, then you say that the problem is well posed in the sense of Hadamard. So this is always we look for existence, we have to, because otherwise there is no point looking at the differential equation. We would like to have a unique solution if possible, and then we would like to know if it is stable, if the solution is stable, namely if you modify the data a little bit, the solution does not change too much. And that is very important because most differential equations cannot be solved exactly, especially partial differential equation. Closed form solution is all not in fashion, or most of them do not admit them, and therefore one would look at numerical solutions, and numerical means you are making perturbations all the time, and therefore if you approximate something, then the solution should not go away somewhere else, okay, it should stay close to it. So these are the three important things we look for. Okay, so that was a quick preview of bird's eye view of what happens in the elliptic case. So now we look at the parabolic problem. For this we need a different technique now. We need what is known as the Fourier transform. So we take an integrable function, that means the integral of mod x over the whole space is finite, and you define f hat xi is integral over Rn e power minus 2 pi I x dot xi, this is the inner scalar product, oops. This is the scalar product in Rn, x dot xi is sigma xi xi, okay, fx. So this is called the Fourier transform, and it is well defined. If you take the absolute value and estimate this integral, e power minus 2 pi xi is of modulus 1, and mod fx integral, that is finite already we know. That is why we need an integrable function to define the Fourier transform. It is bounded by this integral, and it is continuous. That is a nice application of the dominated convergence theorem in measure theory, and in fact it is uniformly continuous also, and it vanishes at infinity. This is what is called the Riemann-Lebesgue lemma. Okay, so these are properties of this Fourier transform. So what are the other properties of this? You take a vector h in Rn, and tau hf is called the translation of f evaluated at x is f of x minus h. So you shift the origin by h, so then you this is called the translation of a function. So it's just a change of origin. Now if you shift a function and then take the Fourier transform, it is equivalent to multiplying the Fourier transform of the original function by e power minus 2 pi I h dot psi. Okay, so that's a nice relation, and in Fourier transform you always have a dual relation. You take the Fourier transform and then translate the function, it is equivalent to taking the Fourier transform of the original function multiplied by an exponential. Okay, so these two are dual to each other, 1 and 2. So here you first take the translation, then the Fourier transform, you multiply the original by a exponential, you multiply the function by a exponential and then take the Fourier transform. It is equivalent to first taking the Fourier transform and then translating. Now if you rescale the coordinates, x going to x by lambda, then the Fourier transform is like this: g hat xi is lambda power n f hat lambda xi. So these are all very trivial properties which you just write the definition and do the calculation, it will come. Yes. Another nice property is that if f and g are integrable, then the convolution is also integrable. Then the Fourier transform of the convolution is just the usual product. So the convolution product via the Fourier transform goes to the algebraic product. So this is a very beautiful property of the Fourier transform. And if f is infinitely differentiable and decreases rapidly at infinity, okay, that is a technical condition which I won't elaborate upon. Then if you take the Fourier transform and differentiate it, it is equivalent to multiplying the Fourier function by a polynomial and then taking the Fourier transform. So then you have the dual also. If you take the Fourier transform and multiply by a polynomial, it is equivalent to first differentiating the function and then taking the Fourier transform. So these two are dual to each other. Multiplication by a polynomial and then Fourier transform is the differentiation, and differentiation of a function and then Fourier transform is equivalent to multiplying the polynomial function Fourier transform by a polynomial. As an example, if you take fx equals e power minus mod x square, then the Fourier transform can be computed explicitly. It is pi to the n by 2 e power minus pi square mod psi square. So it is something like an eigenvector of this operator. If you think of this as a linear operator, the e power minus mod x square more or less remains as it is under the Fourier transform, except for a scale change. The function looks the same. Okay, so why did I say all this? So now I want to use the Fourier transform to solve the heat equation. So you look at the initial value problem, ut minus Laplacian u equal to 0, x in Rn t positive, and u of x0 is u0 of x. So on the x axis I am producing. So in this case the characteristic is the t axis, and therefore I can prescribe data on the x axis and expect to solve the problem. There is no problem, the Cauchy problem has a solution. The previous case was elliptic, there were no characteristics, so I did not worry about. I could prescribe the data on the boundary and hope to solve it. Now the characteristic is the vertical line, so I can prescribe on the x axis initial function, and therefore I have here u of x0. So this is called the initial value problem for the heat equation. So we treat t as a parameter and apply the Fourier transform with respect to x. So ut just becomes u hat t, and now I have Laplacian of u, which means I am differentiating twice, and each time, you know, if you differentiate the a function and take the Fourier transform, you multiply by a corresponding polynomial 2 pi I xi I, okay. So I get 2 pi 4 pi square mod xi square comes there, the I square is minus 1, so the minus becomes a plus, and I get u hat. Mod xi square is sigma mod xi I square, so equal to 0, and I just take the Fourier transform of the initial value. So this is an ODE which we know how to solve, okay. You have first derivative is a linear ODE, so solution comes in terms of the exponential. So you have here u hat of xi t is u naught of xi into e power minus 4 pi square mod xi square t. So if you look at the second function there and look at this, they look similar. So now this is a product of two Fourier transforms. This is a Fourier transform of something, this is a Fourier transform of something. So this is a product of two Fourier transforms, so it is the Fourier transform of the convolution, okay. So that was the property we had before. So if you have the product of two Fourier transform, it is the Fourier transform of the convolution. And then I go back to this condition here, so I put them all together. So I can express u hat as a Fourier transform of this function. So u of xt becomes 1 by 4 pi t to the n by 2 integral Rn e power minus x mod x minus y square by 4 t u naught y dy. So this is the solution of the heat equation with the initial data u0 of x. So using the Fourier transform, we are able, of course there are a lot of justification which we have to do here. I mean, when can we take the Fourier transform, when is all this valid, what are the conditions on u naught, etc. But assuming they are all okay, they are all technical conditions, but we have in general a solution like this. So looking at this, we can immediately draw some interesting conclusions. The first one, if u naught is non-negative, then u of x is strictly positive for all time. So I have a u naught which is non-negative, I am multiplying by an exponential and integrating, taking the convolution, so this will be strictly positive for all time. So this, what does this mean? It is a bit counterintuitive. You know, heat equation is all about heating a bar. Let us have an infinite bar and I heat it. Then I am saying that instantaneously the entire rod gets heated up everywhere. U of xt is the temperature, so if the temperature is strictly positive, so even if I heat in a small portion u naught of compact support, instantaneously the entire rod has got heated up. There is a positive temperature everywhere. So you will probably say, but this does not look right. The answer is no, it is positive, but when you go very far away, it will be so small, so close to 0 that you will not be able to measure it, okay. But still it is positive, okay. So that is the property. So even as you go x tends to infinity, the solution will exponentially decay. So it will be positive, but it will be very, very, very small, so that it is undetectable. So this is called the infinite speed of propagation of signals. So even if u0 has compact support, u of xt will be non-zero when for all x when t is positive. This is the first property. If u0 is continuous, then u of xt is C infinity, even analytic for all t positive. Again, let us go back to the formula. We have a convolution. Convolution has this nice property. If you take a C infinity function and a continuous function and take the convolution, the resulting function is C infinity. Okay, because the convolution has the property that when you differentiate a convolution, it is the same as differentiating one of the components and then taking the convolution with the other component. Now if one component is C infinity, then all the burden of differentiation is borne by that function. So even if you took, for instance, this example of Weierstrass, everywhere continuous, nowhere differentiable function, and then you convolve it with the C infinity function, the result will be C infinity function. So however bad your initial function is, the convolution will be C infinity. So this is with a C infinity function. Here the exponential is a C infinity function. So however bad your initial data u0 is, the resulting function is going to be a nice C infinity function, and in fact it is even a real analytic function. So the result, as a result, the heat equation is not reversible. What do I mean by this? Suppose I gave you originally a initial data, okay, and said how the heat equation temperature evolves. Now if I say at temperature T equals 100, this is what I want as temperature, and find out the initial data. So I want to solve the equation backwards. I can't do it. Why can't I do it? Because I know that given any initial data, instantaneously the solution becomes analytic. So at t equals 100, it must definitely be some nice analytic function, and even I cannot prescribe an arbitrary analytic function. There are several properties it has to satisfy before it can qualify to be a solution of the heat equation. Okay, so I cannot give an arbitrary temperature at t equals 100 and say produce for me an initial condition for which it will reach this in that time. So the heat equation cannot be reversed because of this infinite smoothing which happens immediately. Okay, so now let us move to the third one, which is the wave equation. So now we have n equals 1, like with the initial value problem, utt minus uxx equal to 0, u of x0 equals fx, and ut of x0 equals ex. Again I am prescribing data here. Why? Because the characteristics are these two lines, x plus t equals constant and x minus t equals constant. So lines like this are the characteristic. So I am prescribing the initial data only on the x axis, and therefore now if I here, so for the Laplace equation we just straight away integrated. For the heat equation we use the Fourier transform. For the wave equation, in each dimension we will use a different technique. Okay, so that is the thing becomes more and more complex as we go. So we first in one dimension, namely one space dimension, x here varies just, oops, okay, so this is on, yeah, x is in Rn, n equals 1, so x is in R, okay. So you make a change of variable, x equals xi plus t, xi equals x plus t and eta equals x minus t, inspired by these characteristics here. And then if you substitute and rewrite this equation utt minus uxx, in the new variables it just becomes u xi eta equal to 0. So the derivative with respect, second derivative with respect to xi eta is 0. So this means this is a function if you work back and integrate this equation u of xi eta equal to 0, it's a very simple exercise to see that u of xi eta should only be a function of xi plus a function of eta. It can't be anything else. Can't be, you can't mix them. So if you go back, u of xt will be f of x plus t plus g of x minus t. At t equals 0, so we now apply the initial condition. So at t equals 0, fx plus gx equals fx, which on differentiation will give you f dash plus g dash equals f dash. Okay, just keep it aside. Then there is a condition on the derivative, ut of x0 equals g of x, and that gives me f dash x minus g of x, g dash x equals g of x. So we have f dash plus g dash equals something, f dash minus g dash equals something. So we can get f dash and g dash separately and then integrate it. So if you do all that algebra, you will get u of xt equals 1/2 of f of x plus t plus f of x minus t plus 1/2 integral x minus t to x plus t g of xi dz. So this is the solution of the initial value problem in R space, one space dimension and one time dimension. So this is called the solution of D'Alembert. Okay. So now let us look at the properties of this. U is only as smooth as the initial data. So if you look at this thing here, you have just f here and then g. So if the function cannot be better than the smoothness of f. So you saw in the heat equation, if you have initial data, instantaneously the solution became analytic. In the hyperbolic case, it just stays there. I mean, whatever smoothness you have initially, that will be propagated, because along the characteristics singularities are propagated. So you can only expect smoothness as much as this. The values of u at xt depends only on the values of the initial data in interval x minus t, x plus t. So you see here, u of xt is f at x plus t and x minus t, and the integral of g on the interval x minus t, x plus t. So you can prescribe f and g all over the real axis, but if you want xt, so I have point xt here. I look at the two characteristics which pass through this point. So this is x minus t and x plus t, okay, and whatever may be f and g elsewhere, it is only the values here which are going to influence the value of u at xt. So this is called the domain of dependence. So this depends only on this. Similarly, if you have a point here and look at the two characteristics which emanate from it, this value will only influence at time t the solution somewhere in the neighborhood of this interval. So that's called the domain of influence. So that's a direct consequence of this formula. That's what I just said this. So in particular, if the initial data has compact support, then at every time t, the solution also will only have compact support. And this is again in contrast with the heat equation, because there initially, even if you had compact support, instantaneously the heat spreads everywhere. Whereas in the case of sound or light, if you have initial, this is in one dimension of course, so if you have initial data of compact support, at every time t, the disturbance is localized to some compact set. Beyond that, it has no influence whatsoever. So you have, this is called the finite speed of propagation of signals. So signals can't spread with infinite speed. Okay. So now let us, so this is one dimension. So now we want to go to 3 dimensions. for deliberately I am skipping 2 dimension, so I am going straight to the 3rd dimension. So you take a function h and define what is called a spherical mean, namely the average of the function on a ball of radius r, center x, and so this is the average which I have written there. Now just as I did in the case of the elliptic thing, it is the same arguments, so you can change to a fixed thing and then differentiate. If I want to differentiate this function with respect to r, then r occurs in the boundary, oh no, r occurs in the boundary, so I can't differentiate it, so I change it to a fixed boundary and then I can do whatever I like. Then using again Gauss theorem and so on, just as I did last time, you can now get an equation here. This is the Laplace, this is the Laplacian in polar coordinates for a radial function, so that's just that part here, and this is the Laplacian in x. So if this can be explicitly computed starting with this formula here. So this is called Darboux equation. Now you take the solution of the wave equation with the initial data as before, treat t as a parameter and form the spherical means. Then you can recover the original function from the spherical mean by taking r equals 0, namely integrating over spheres of radius 0, which means you just have the point to punctual values and therefore you get back the function. So we will instead look at this rather than this. And initial values also, initial data, Cauchy data also has this. If you take the spherical means, you get all this. When n equals 3, a miracle, it's a very special case. So d2u m by d2u t2 is d2 by dr2. This is the Darboux equation, and this came because of the Laplacian. The Darboux equation, this is what we put on the left hand side. Here this is Laplacian x of mh, but that is nothing but dt2 by, because u is the solution of the wave equation, this becomes a time derivative there. So that Laplacian gave you this, and the other side with n equals 2 gives you this, which is nothing but d2 by dr2. So you get a one dimensional wave equation for RMU now, which we know how to solve. So we can write down the D'Alembert solution. Which is this formula here. This is just exactly the solution which I wrote for one dimension. And then as r goes to 0, we know that we recover u from this, and these two, this quotient becomes the derivative here, d by dt of tmf, and this, when you put r equals 0, gives back the value at t. And now you can rewrite it in proper way. Go back and you can, what is mg, what is mf. So if you use the definition, then you get this expression for the solution of the wave. So this is the solution of the wave equation in 3 dimensions. So what are the properties of this now? If f is in Cs and g is in Cs plus 1, then u is in Cs minus 1, because in the final solution I have to differentiate f a little bit. So there is a loss of one order of regularity in this case from the initial data. So if you started with Cs, s times differentiable initial data, solution is only s minus 1 times differentiable. So even between the case n equals 1 and n equals 3, there is a difference. In the n equals 1, what did I tell you? The solution is as smooth as the initial data. If it is whatever it is, f was sitting there like that, and therefore, but if you go to n equals 3, in fact for all higher dimensions, it in fact is a little less smooth than the initial data. This is called the focusing effect in higher dimensions. Now look at the domain of dependence. It is a surface, mod y minus x equals t, because everything depends on the values on that surface. So it is now a surface, not a solid region. Previously in one dimensions it was an interval, it is a solid region. Now it is just a surface, it is just the boundary of a solid region. And if f and g have support in a ball of radius rho, then u of t has support in a spherical shell which is between the ball of radius t minus rho and t plus rho. So this is again the solution is of compact support, but this has a very interesting consequence. This is what is known as Huygens principle in physics. So the support is between two shells, two spherical shells. So and this radius keeps expanding. So for all time, for all points, there will be a time when it will come out of the inner radius and sit here, okay, because these radii are expanding as time goes. So given any point in space, eventually the solution will become identically zero there. So this is called Huygens principle. For instance, I am now talking, so sound waves, light waves, these are all carried by the wave equation. So if I stop talking now, after some time you won't hear me, which is good. Otherwise, imagine all the sounds keep accumulating in your head, then what? Similarly, if you switch off the lights, you won't see light after some time, it won't just accumulate, okay, and that is because this support of the solution keeps increasing, expanding, and therefore given any point, sooner or later it will come inside the inner circle, and therefore the solution will die out completely. And initial data has compact support, then the solution is of course compact and expanding. I have just explained that, and the solution decays with time. So even though it is now in a very big compact set, the solution will be quite small because the energy is conserved. There is something called conservation of energy of these things, and since the same energy has to be distributed over a bigger set each time, so it has to be more people to feed, less food you get. So it is the same principle. So solution will decay with time. When do we stop?
10:30.
Okay, so then I should wind up fast. Okay. So this is called Hadamard's method of descent for n equals 2. So I went from 1, I went to 3 using some trick of calculus. Now I am coming down to 2. How do I do that? I treat n equals 2 as a special case of n equals 3. Namely, I imagine that the Cauchy data does not depend on x3, and then I take the solution on x3 equal to 0, and then I produce. So this time I will get a solution. And now if you look at the domain of dependence, it is now again a solid region. So like in one dimension, in two dimension also it is a solid region. So this Huygens principle won't work. So for instance, if I have a water, I throw a stone, it will make ripples, it will make waves. Now after some time, for the naked eye you will think the water has settled down, but water will never settle down. There will be oscillations inside, disturbances inside, but so small that you can't detect it. It's just like the heat equation, as I said, instantaneously it gets heated up, but you can't really feel it because it's too small, far away. Similarly, these disturbances, because the domain of dependence is now a solid region, once a disturbance, always a disturbance, but it will die down in time, and so you can't feel it. The decay in time is there. Next is, of course, I will just not talk about this because I don't have time, is the separation of variables. So this was another technique where you look at, break the equation solution into function of x and function of t and try to solve it, and this is what gave rise to Fourier series. Okay, so this is how Fourier series were born, and there was a huge controversy for nearly 75 years in Europe between 1750 and 1820 or so thereabouts, because on one hand you had the Fourier series solution given by Bernoulli, and he did it even before Fourier for the wave equation. Fourier did it for the heat equation, and they said the function can be expanded in terms of sines and cosines. and on the other hand you had D'Alembert's solution, which was general solution, and Euler objected, saying how can any function be written as the sum of periodic functions and so on. So they were all fighting all the time, till finally Dirichlet told what is meant by convergence of the Fourier series, when will it converge, etc. And in understanding all this convergence, the Riemann integral gave way to the Lebesgue integral. One had to understand the nature of infinite sets, countable, uncountable, all these things came up. Lebesgue integration came in to replace Riemann integral and all that. So this not to be taken lightly. Okay. And in higher dimensions you get what is called an eigenvalue problem, and the study of the eigenvalues of the Laplace operator is itself a separate topic for discussion. It's a beautiful confluence of geometry, analysis and PDEs. So I will just say only that, since I don't want to hold you up. Finally I will come to a nonlinear equation called Berger's equation. So this is called ut plus ux equal to 0 with the initial data. So a characteristic curve now I define as a solution of this differential equation here. These two buttons are so close forever. That's why I didn't want this. Okay. So now if you can solve this equation, and then along this characteristic curve u is u of x t t, so differentiate du by dt, it becomes ut plus ux x dash, which is ut plus ux equal to 0, which means, which is the equation itself. So u is constant along a characteristic curve, so this becomes a constant. If this is a constant, then the solution will be x naught plus u naught x naught t, which is immediate, because dx by dt equals a constant, so we are just getting straight line. So how do you solve the problem? Theoretically I have solved it. Take any point xt, and I just have to look at the characteristic curve passing through that point. I slide back, whatever is the initial value here, that is the same value here. So that is what this equation says. Along a characteristic curve, the solution is a constant. Of course I don't know where these characteristic curves are unless I do it. So no, in fact I know it, because at each point I take the straight line of slope u naught of x naught. So that's all. So, but this is not as simple as it looks. Sorry for this bad picture. Let me take an initial data which is 1 in the negative axis and 0 after 1 and some nice smooth function here. I draw the characteristic curves. So here dx by dt is 0, so the characteristic curves are vertical lines. Here dx by dt is 1, so the characteristic curves are like this. Now you take a point P like this. Now which way am I going to slide? Do I slide like this or do I slide like this? I don't know. So that means the solution very rapidly develops discontinuities, okay, and they are called shocks. So for instance, this is a typical prototype of the study of the flow past an aeroplane. So if you want the aeroplane to fly properly, we have to study equations of this kind where shocks are going to develop because of what are called equations like these, which are called hyperbolic conservation laws. So up to now we've been looking at a solution of a PDE as a classical solution, namely it has as many continuous derivatives as the order of the equation. But now we are forced to look at, generalize the notion of a solution where even discontinuous functions may be interpreted as a solution. So that is the beginning of the theory of distributions. That's a completely different story, and it's therefore a good point to stop. So if things which I have said today can be found in these two books, for instance, there are many books, I just picked two important ones. Thank you.